Okay. Supposedly I am recording. There we go. Okay. I know that you're getting mixed messages on the due dates. I'm going in and trying to change the due dates, and some of them it lets me, some of them it does not. But on our schedule, the printed schedule that I printed out at the beginning, it's not necessarily it's on the syllabus as well. But I am going to cancel the project, like the randomization test activity, which is supposed to go out next week, um, as well as the proportions activity. Yeah, I'm gonna either I'll demonstrate those or I'll just forego them because it's coming down, not necessarily down to the wire, but I feel like those projects somewhat distract you. And those are seriously not big projects. Differentiating between statistical and practical significance. We can have a chat about that and we've got it covered. Um, okay, so today on our schedule, April 9th, we're to be covering 10.4 and 11.2, which I think we're going to get through that very quickly, especially 10.4. 11.2 is a new concept, but I don't think you're going to find it difficult. So I want to cover that, and then I want to give each of you, I want to work with each of you on ideas for the final project. Anyone who is not attending and who is watching the video today, um, I would like to, actually, I should probably take a screenshot of who's here so that I know who I need to contact and set up an appointment to do a discussion on that. Okay, got that. So now I know who I need to harass. Okay, basically, I am not having you do 10.3a. Simply because it's a little confusing the way they've demonstrated it. Although I do think that StatCrunch has made some upgrades, and I think we can put in a more robust formula. But nonetheless, if I get around to demonstrating that again, I plan to demonstrate that again. Just looking on down the line, we're going to have activity where we're doing more randomization in section 11 point, I believe it's 3A. Yeah, 11.3A, I'm going to cancel that as well. Just I will demonstrate it. I don't think that's anything you have to show competency on. It's not covered on the exam 3 anyway, so I'm just going to forego it and we'll go with a demonstration, follow along with that. Okay, do you guys have any questions before I get started?
Actually, I do.
Okay.
So for the 10.3A, it didn't
Mhm.
allow me to open it like on StatCrunch on the interactive.
The homework or the interactive?
Actually,
Oh,
both.
I deleted both because again, it just came down to I think the instructor or the author, his demonstration where you're adding each individually is tedious. Um, I don't think it's something that you guys have to practice. I'm going to demonstrate again today and we're going to talk through it together. So hopefully that'll be enough interaction without the frustration of knowing you have to take a screenshot and am I doing this right? And this StatCrunch going to accept my answer? Am I rounding it off correctly and all that good stuff? Does that kind of make sense?
Yes, thank you. I just wanted to make sure I didn't miss anything.
No, no, I get it. It's got to be kind of confusing, and I kind of wavered on making that decision. I do have to say that it is something that you need to be aware of, that if you are going into anything, I would say anything that is going to involve any kind of research, if you're ever interested in that, I can guarantee you will come across um, bootstrapping as a process that you would be using. But chances are you're going to be using a totally different software. I would say the SASS and the R are probably the two softwares that are utilized in most universities' research departments, no matter what kind of area you're in, they're utilizing that software. So I don't see why you have to wrap your head around the specifics of how to use StatCrunch, because chances are, if you move on, StatCrunch is more of an introductory software tool. You'll be going into something far more robust with a lot of other functions. Does that kind of make sense? I just really want to demonstrate, make you aware of the process and why it is valuable. Okay, so I'll go, should I just start with that, the 10.3a? Do some practice problems from that?
Sure.
I think we will, being that's what you guys are concerned about. And it does make it feel a little bit better knowing that you don't have to do them, right? Okay. I'm going to start sharing my screen. And the other thing is that we have done not bootstrapping, but we've used the applet in section 9 or chapter 9. And actually, I think we use the bootstrap method for finding, oh, I got 3 screens and everything pops up on a different one here. Sorry, I just want to get it within my field of vision here. Okay, I should be sharing, you guys tell me, are you seeing my screen where I'm showing the homework for 10.3a?
Yes.
Good, because I'm not seeing that on my screen. Which of my screens is showing? Okay, I'm going to go ahead and open up the first one. I don't think I did this one with you. I did another example from our worksheet on Monday. So actually, I do want to see that instructor tips. So I'm going to go back, continue. We're going to go back. Okay, it says to recalibrate, blah, blah, blah. Remember to add the expression, 397.6. I'm going to see if I can put that somewhere. Hint, click the 3 bars, blah, blah, blah. There's some great tools here, but I'm going to go ahead and shrink that down. Make this a little bigger so we can see our whole thing. Okay, Coors Field I did do this one, didn't I? The Colorado Rockies, or no? I'm sorry, this author is really into baseball, so he pulls a lot of data examples from baseball. Okay, Coors Field is home to the Colorado Rockies baseball team and is located in Denver, Colorado. Denver is approximately 1 mile above sea level, and the air there is considered thinner. Therefore, baseballs are thought to travel farther in this stadium. Does the evidence support this belief? In 2018, the mean distance of all home runs hit was 397.6. The following data represent the distance in feet of a random sample of 12 home runs hit in Coors Field. Now, I wish he would have made this more clear, but in 2018, the mean distance of all home runs hit in the National, League or whatever would make that more clear. But this following is just a sample of 12 from Coors Field alone in Denver. We are to use a bootstrap approach to test whether the balls travel farther in Coors Field. So I'm going to go ahead and open this in StatCrunch. And so this is our data. And it's a small data set. And this is, I guess I need to reiterate, this is why this process is so valuable. It's kind of been developed over the last 20, 25 years. And really, it's developed out of the fact that we have computer modeling that we can do. We don't have to wait for 35,000 people to come down with this rare disease to have enough samples, to do random sampling and experiment with different so forth. We can have a small sample and of patients and try a new tool or method of treatment and see if we can impact things with just a small sample. Because we can take data and go into StatCrunch or any software, and we can recreate by bootstrapping a far bigger sample to see how the results would work out if we had a larger sample to compare against the population. So we know that larger samples are better. And that's basically what we're going to be doing here. Okay, so all baseball or all home run hits, the mean distance of all home run hits is 397.6 feet. We've got the sample of 12 home run hits. I need to find the average here because I'm going to manipulate this a little bit. So I'm going to go ahead and click stats, summary stats, and I want columns. And all I care about is just clicking var1. And all I want is I just want to know the mean of the sample. That's all. So I'm going to go ahead and do that. And I need to find my calculator. We come up with a mean of 412.25. And you're thinking, yeah, that's farther than 397.6, given this sample. But again, it's a small sample. And I'm going to just kind of set that down below here because I don't want to confuse it. This is my sample mean down here. Okay, so now I'm going to go ahead and I've got to figure out, I've got the sample mean here, and I think I figured out a way to do this without getting too crazy. I'm going to go ahead and click this var1, I guess I'll call it recalibrated. And being I'm highlighted in there, I'm going to go ahead and click on data. I think this will work. If it doesn't, I'm going to go back to Excel because I know Excel, how to operate that. So I'm going to click compute an expression, and I can see that this mean is higher. So we're thinking these are all going to be higher. I need to create a data set that is has a mean of 397.6. So if I take my calculator, and this is what you need to have a calculator handy. We're going to take 412, this higher mean that I have, which is 412.25, and I'm going to subtract the mean from the entire baseball league, the league average, which is 397.6. And I see that this mean from this sample set of 12 home runs hit in Coors Field is 12.65 miles farther, or feet farther. Yeah, miles, sorry. Feet farther than the average from, but I'm going to recreate another sample. So I'm going to, or another, recreate this set. I'm calling it calibrated. And I am going to take the mean of, I think I want to say var1. And I'm going to add, or no, I'm going to subtract the difference, the difference between the means, which we said was 14.65. And I want to see if that will work. Huh. Let me click. Oh, you know what? I'm going to click the build, use the build. I'm going to say var1 minus the, I guess I have to do it on here, 14.65. So I'm going to lower, you're like, what? How do I know what I'm doing here? Yay, it's going to take it. And we're going to call it recalibrated, or I guess I had them there from last year. Okay. How do we know if we add or subtract? Oh, it didn't work, guys. I'm sorry. I tried. I'm going to delete this and delete this. And I'm going to go back to copying this. I just think this is faster. By now, Mercy, I know you like to do all the adding and subtracting yourself, but I'm going to go ahead and open up Excel. And that, again, that's something that a different spreadsheet or a different software tool probably would do. So I'm going to go in here, copy the data from, this is Coors, and I'm going to make this bigger. I am going to go ahead up here in the next cell and I'm going to put in the equal sign, and that's a clue to Excel to calculate. And I want it to take the value that is in A1, cell A1, that 427, and I want it to subtract the 14.65, the difference between the Coors, this mean and the mean of the entire league. So I came up with that value, and I can go back and click on that value so that the square is around that. But I see this little cell here in the lower right corner. If I grab that and pull that down, I'm telling not StatCrunch, but Excel to recalculate all of these values in A, column A, go ahead and subtract 14.5 from that. So I've done that, and now I've got recalibrated data. So I'm going to copy this, and I'm going to close that down. I'm going to go in here and call this, just go ahead and paste it in. And just to make sure, I want to go ahead and take stats, summary stats, columns, and go to var2. And I want to make sure I've got the same mean as I got in that first column. So I click compute, and yes, we have 397.6. We've recalibrated the data from Coors Field, added the difference so that this new data set has the same mean. We've adjusted these means. So now our data set is mimicking the regular whole, all of the, it represents a sample from the entire population of home runs hit in the major league. It has the same range and standard deviation as this original set. So it's retaining some of that characteristics from the Coors set, but it's now readjusted to the mean and centered more equivalently to that. So now we can look at this and say that, hey, this is a comparable collection of data from the entire baseball league. Their set of all however many home runs were hit in that particular year. So now we can use that. So we're going to go into applets, and we're going to go down to resampling, bootstrap. We still have the problem that we have such a, we're going to use var2 because that's where our recalibrated data is. And I think on here, oh man, I have to go in here and I determine the null and the alternative hypothesis. The null is that it is equal to 397 feet. Was that what it is? 397.6. And the other is that it is greater. We think it's going greater, 397.6. And so I can go on, check my answer. Great. The mean of the sample, this is my mean down here, 412.25. Just one. Not have to do with this. Okay. Get that done. Okay, so now I've got my information about the seed that they want me to use. Okay, so I'm going into Bootstraps. I've identified var2. I'm going to leave my statistic at mean, and then I'm going to use the fixed seed of 12,250. And that's what I use. So I click compute, and we've seen this applet before. We now are going to run samples of 12 1,000 times twice, so for 2,000 times. So we're really exaggerating the number of home runs hit, is kind of what we're anticipating to do here. So we end up getting this thing right here, this histogram looking deal. I just want you to recognize that the author does a different method where he just really likes using all the different menus, I guess, in StatCrunch, where you go and you copy that column. This is the column of all the runs. He wants you to copy that into the spreadsheet and then go into histograms and create. It's like it doesn't need to be that hard. You can come down here and click on these bars. There's 3 bars down there, and we can click on dividers and percent, and we don't have to recreate another histogram, we're using this histogram, but we now have our dividers. So I'm going to actually, I need to leave this divider here. I'm leaving this divider over here because going back to how we did our null and alternative hypothesis is we are speculating that it's greater. So we're putting all of that variance, or I shouldn't say variance, but all of that error that it's going to be greater out here. So we're making this tail actually bigger because we don't have it, we have no speculation that it's actually lower than the average. We don't have any tail out here in the left that we're concerned about. We only want to look at and see if it's greater in that right tail. So that's why I'm leaving this out here in the edge, and I'm double clicking here, and I am going to put, again, this data is normalized according to the league. Make this bigger because I really want to see, this is my mean down here for the, I want to know where our data, this is Coors Field data mean here. So we want to know what are the chances of having a mean that's way over here. So I click that and it's got some random number because I just went anywhere. So I'm going to put in the 412.25 and I want to see what are the chances of that average being the average for the entire league. Where does that fall with this whole span of averages from the league? We did this 2,000 times. And yeah, there's going to be some variation. That's why we do that. So we click compute and we're like, whoa, over here, this value that we got with our mean from Coors was 412.25. That is way out here in this tail. In fact, only 1.5% of the home runs hit by the entire baseball league traveled as far as the mean of this set of Coors home field runs. Okay, so that's where we get the 1.5%, which you're going to be, that's your p-value, but we have to write that in a decimal format. So I'm going to put that down to regular size here, and we're going to come over here and continue under sample, select the column of recalibrated data, then click mean. It was already selected. The seed is going to be, I'm doing this all twice, I'm sorry. Used fixed seed. Where is it at? 12,250. So you feel like you're just putting everything in twice. Click compute, click 1,000 times twice to get a 2,000 sample, and then we're clicking analyze. So we've done all that. I don't know where the rest of it, why, did I check answer? Okay. And we find the p-value is this over here in percent form, but I'm going to write it as 0.015. And this p-value is the message that I keep getting that StatCrunch, MyMathLab, something is not accurate on this. So we might not get exactly what we need. And I'm finding that from when I've checked students' work and stuff in the past, we're close enough. Okay, write the conclusion to this hypothesis test. So we're comparing that p-value to 0.05. This is farther out in that tail because 0.05 is probably right in here somewhere. Okay, so we're going to say since the p-value is greater than or equal to what we are going to reject the null hypothesis. It is not equal. Anything that's out here in the tail is unlikely to happen. And here it happened. So there must be something going on with that air up there. There is sufficient evidence to conclude that the home runs in Coors Field exceed the national mean of blah, blah, blah. Of the National Football League. Okay, one or more. What did I do? Maybe they're changing insufficient and they're saying are equal to. No, it's greater than. This is less than, I'm sorry. I was right the first time down around and I didn't catch that I put the wrong thing in there. There we go. Final check. Finally, we got it right. Okay, so that kind of, you're supposed to show your work on that. That's as much as I want to review that, unless you guys have questions that you want me to do another one. What's your thought? Okay, can anybody tell me what the purpose of bootstrapping is? Give me some information about that. Just what does it allow you to do? No one? We're all chicken here today. Bok, 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 bok. No, I think I'll do another one then. Okay, so I'm going to another one. This is saying download, show work, all so forth, but you don't have to do this one. So the mean waiting time at a drive-through, I hate this one. Okay, at a fast food restaurant from the time an order is placed to the time the order is received is 84.3 seconds. A manager devises a new drive-through system that he believes will decrease the wait time. He initiates the new system at his restaurant and measures the wait time for 10 randomly selected orders. The wait times are provided below. We're going to complete parts A and D. I'm going to show this completed so I can talk through it faster than having to put. Okay, so I have this completed now. So I want everyone to be able to write the null and the alternative hypothesis. Okay, the mean time is 84.3 seconds, and he thinks he's devised a plan that he's going to reduce that amount. So his hypothesis for this set of data is that this mean time of service is going to be less than 84.3. So that's our goal there. Population is not available for wait times prior to the invitation of the new, therefore that he will choose to use a bootstrap method. Basically, we don't have any previous thing that we're comparing this to. I shouldn't say that. So we're going to basically go ahead and do the bootstrap method. How can the data be recalculated? So I need to open this up. You guys don't mind, I'm going to move this over here and make this much smaller so that I can see my whole screen here a little better. Okay, so there's our data in StatCrunch. And this is from his new system. So I'm going to go ahead and find out what is the average time in this system. So I'm hitting summary stats, columns, wait time, and all I want is the mean. I just want to know what this time is. It's 78. So I need to compare that to the 84.3. Well, 84.3 minus 78 is actually 6 points lower, but he needs to take this data to get the same spread of data, the same standard deviation, and he needs to add that difference here so that this new column of recalibrated data is going to have the same mean as the 84.3. So again, I'm going to go into, I'm going to go in here into Excel. I'm just going to create a different column here. And I'm going to copy and paste. And then I'll call this enter. And here I need to say, I'm going to do the equals. D1 is the cell location for that first value. And remember, these were lower. So I need to add, what did I say it was? 6.4? Okay, so 6.3. Then I click enter, and that's adjusted that one. So now I can go back up and I can add to all of these. So at first glance, you're like, they keep doing that. They put the first one a really odd one, and all the rest of these are much lower. So you can see why you're adding and not subtracting. That first one, your first inclination is, oh my God, that's much higher. I'm going to have to take that and adjust. But anyway, so this is our new data, recalibrated data. So I'm going to cut that out or copy that, close that down, put that back into StatCrunch. And if I want, I can go up here and say recalibrated. I'll just leave that. Calibrated data. So I'm going to click that. And now just to make sure that I did this correctly, I would encourage you to go into stats, summary stats, columns, and grab your recalibrated data and click the mean. And we want to double check. Did we come up with the 84.3 that he had in his? And we did. So we've recreated, use this original set, recalibrate it. So now we have a set of 10 times that has the same mean as the original, as the average from the industry or whatever. And then we're going to use that, we're going to use that data to do a bootstrapping technique. So I'm going to go into applets, down to resampling and bootstrapping. And I want to select my recalibrated data. I'm going to leave it on the mean. I'm going to use a dynamic or a fixed seed. What do they want me to use here? So here they kind of tested us on, do we add or subtract? And so we subtracted there. And this is what, at first glance, you'd think you'd be typing that in, that it would take that, but it doesn't. So you'd have to do each one. Sorry, I keep going farther enough. Okay, so I'm using the seed of 11 to 89. And the whole purpose of that fixed seed is so that we all get the same answer and that they'll be able to, my math lab will be able to check our work. And I need to click 1,000 2 times because I need to have a minimum of 2,000 samples to have a better view. So now we're looking at, this is the distribution of normal data from the entire population of wait times at fast food restaurants or whatever it might be. So this is the whole population. And so we want to know this data set for this new method that he came up with. Where does that mean time fall in this histogram? And so I'm going to go down to the 3 bars here because I want to analyze. And I'm going to click dividers. And again, I want percent. So I'm going to hit OK. And so I'm going to leave this over here because actually I need this because going back up here, I'm testing to see if I have something less than 84. This is the distribution of all the means of 2,000 means where the mean of the means is 84.5. So I'm testing to see if we have a result down here. So I'm going to go and move this all the way to the edge. And I'm going to bring this over somewhere in here. I wouldn't even probably have to do that. But I'm going to go ahead and click on this. And that value where I clicked is 81.3. But I want to check to see where would an average of 78, a data value of, I should say, a mean data value that would level out at 78. So when I click compute, I end up getting 6.9, which would be, this is where I hope, I'll come back to this, 0.069. We're moving that decimal 2 places back to the left to write that as a decimal. Okay, so I think I can make that bigger. But going on down below, the way that we interpret that is since the p-value is greater than, this p-value is greater than our alpha that we are testing against, 0.05, it didn't fall in that tail to the left of 0.05. We do not reject the null hypothesis. There is insufficient evidence to conclude that the new drive-through system will decrease time. Now, the thing is, in the past, you know, there are papers written about p-value of 5 being the cutoff, 5% in the tail. Well, it all depends on what your application is here. This is just wait times. I think if you got somewhere in the 10% range, between 5 and 10% says that you're having impact perhaps. If you were in, it depends on the application. If you're doing something where you've got you're doing medical work and there's lives at stake here, then yeah, maybe 0.069, you want to be closer to 1%, not almost 7%. It all depends on that's how you determine that ahead of time, what your alpha is going to be at. Okay, so that was the second time through. Something I wanted to point out, this question right here is kind of crazy. They're build the null, blah, blah, blah. Choose the null model that would be used to simulate. So on that screen that looked like this, you're to decide what did we choose here. The null is, in this case, the 11,289. That's nothing they fixed here. A lot of these are just changing the mean. That's the correct answer, or that is correct here, and that is C. Whereas I should have chosen something that would have been. This is another reason why I decided I'm not making you go through this. This is the mean. Did they keep grabbing which one is the right? You didn't click the fixed seed. So this isn't the right thing to enter. To me, that is got to be a very frustrating activity. I didn't want you guys to go through that. So I felt like demonstrating it. Now, can I see some thumbs up if you guys are okay with that I move on to the new meat of what we're doing today? Please tell me you're all good with this.
I have a question.
You do have a question?
Yeah.
Okay.
How do you know that you're supposed to click either the right or the left divider?
Okay. You choose the right or the left based on this sign here. We're looking at the tell because it's pointing to the left here. We're looking to see if it's going to be less than. That's how we decide. We're only looking at this. If our problem says we think it's greater, then we're going to be looking at the right side. If our problem says we just want to know if it's different, what are the chances of getting something as extreme as this, then it could be below or above. So you'd want to split this, you'd have a lower tail and an upper tail that you'd be looking at. Does that answer your question?
Yes. Thank you.
Okay. Anybody else have a question? Okay, again, you're not going to be tested or needing to show proof that you know how to do this process. Yay, right? Okay, I'm going to go ahead and close down. I might use StackCrunch here in a bit. Okay, so the next thing that I wanted to do is go into today. I'm hoping that all of you watched the interactive activity for 10.4. I want to open that up here. Not the interactive, the homework. Well, I'm hoping you watched the interactive, but I'm going to do some homework here. Do you guys see a new screen on things that we are going to do? There's only 3 questions in 10.3, and in all honesty, it really does just review where we've been. Okay, so on 10.3, this is, or I'm sorry, 10.4, you're just identifying. We're just identifying, our test stat using, okay, a psychologist obtains a random sample of 20 mothers in the first trimester of their pregnancy. The mothers were asked to play Mozart in the house at least 30 minutes each day until they gave birth. You know what? I'm going to change this up so I'm not doing the same ones that you guys have to do. It's random. The more times I do this, you have a smaller percentage chance of getting it. Okay, the psychologist, 20 sample, mothers are asked to play Mozart at least 30 minutes each day until they give birth. After 5 years, the child is administered an IQ test. It's known that IQs are normally distributed with a mean of 100. Perfect, that's nothing different. If the IQs of 20 children in the study result in a sample mean of 103.8 with a standard deviation of 14.7, is there evidence that the children have an higher IQ? So in 10.4, you're learning, hey, which one of these do I use? We're talking about a sample mean. So I'm going to open up, get more help. We're going to go into StatCrunch. And I want somebody to tell me, we're not going to be doing the applets. We're not going to be doing the bootstrapping. I'm going to be taking the quick, fast, and furious method. But am I dealing with proportions or am I dealing with mean? Very quickly. It's one of those two. Anybody want to help me?
Mean.
Mean. Okay, so that means I'm going to go into stats and I'm going to go down to t-stats because we use t-stats to evaluate mean. And I'm going to hit one sample. And this time we have summary. We have the mean and the standard deviation and we know our sample size. That's summary information. So I'm going to click on summary and I'm going to do my mean of our sample mean. All of this information is from the sample at the top. I'm going to put in 103.8. And then my standard deviation was 14.7. And our sample size was 20 mothers. And so that's our mean. We're testing to see if the mean is equal to 100. And what are they asking? Is there evidence that the children have higher IQs? So we're testing to see if there's higher. What sign do I need to select here? The one that goes to the left or to the right? Points to the
To the right.
right. That's the one that's greater. The left is the one that's less than. So I've identified what I need. I'm not doing a confidence interval here. I can go ahead and click compute. And so this is way faster, easier, but we have a large, we don't have a large sample, but we're told that we know that the sample of all IQs is normally distributed. They gave you that phrase right here. IQs are normally distributed. So if as long as it's normally distributed, it doesn't matter if it's a small sample size. We're good to go. We can use this method. This is the quick and easy method. So we came up with a p-value of, there's our null, and we're using the t-distribution because the parameter is the mean. We know what the, we assume that it's normally distributed. Then our test stat is right here, this t-stat. That is basically the t-score for our data, where the mean of our data fell. And then our p-value is this 0.131. That is the probability. If I move that decimal over 2 places, we've got a 13.1% probability of getting something more extreme than this outcome. In other words, is this in my tail? I'm comparing this p-value to our alpha, which is 0.05. Well, 0.13 is in the normal range. It's not more extreme than 0.05. It's not in that tail. So we are going to fail to reject the null hypothesis or do not reject the null hypothesis. There is not sufficient evidence at this level that the significant, that leads us to believe that mothers who listen to Mozart have children with higher IQs. It's getting close to being interesting, but that by itself isn't going to guarantee a high IQ. So that's how you would go approach that one. And this one, we are looking at a scenario here where in 1945, an organization asked 1,528 randomly selected sampled American citizens, do you think we can develop a way to protect ourselves from the atomic bomb in case others tried to use them against us? With 825 responding yes. Now, clearly, this was something that was actually done. Did a majority of the citizens feel that the country could develop a way to protect itself from the atomic bombs in 1945? And we're using an alpha of 0.05. So the big question is, if you didn't have this outline to go by, you would be filling, in fact, you're going to be doing that for your homework, filling this in. Is this a P? I mean, you've got options. I can't even show you the options because I selected so that I can see all the components here. But you've got to figure out, is this proportion that we're looking at, or is it mean? And this is clearly, we're looking at a proportion of people met the criteria or did. And when our criteria met the criteria that they felt confident that we could protect ourselves. So the null is going to be equal. And we're asked, did the majority, so this word right here, says that more than half. So we're saying that it could be equal. I mean, the null is that it's equal to half, and our alternative is that it's greater than half. That would be the majority. So I didn't even do that over here. This is a different problem. So I'm going to go, where do I go over here in stats? Is it t-stats or proportion stats?
Proportion stats.
Very good. So I go to proportion stats and I have one sample and I have with summary. Okay, the number of successes was 825. The number of observations was 1528. And I'm looking to see if it's equal to 0 or greater than 0. So we're going to go ahead and hit our deal there. And we find that, wow, our z-score is 3.2. And we know that normal, usual z-scores fall between -2 and +2. This is actually +3. That is way out in the positive range. So Americans were confident that Americans could, or that America would be able to defend itself and protect itself from atomic bombs. That's what we're getting out of this. And so that's what they mean by the z-score. I know that we didn't talk about calculating that at all, but I think it's kind of important that you know that that's just really the z-score from our data. And then our p-value is very, very small. It'd be 0.001. Looks like these are calculating correctly. The p-value is less than the level of significance, so we are going to reject the null hypothesis. We know that it's not equal to 50-50. It is, there is sufficient evidence to conclude that an actual majority, more than 50% of the country, feels that we could develop a way to protect ourselves. Okay, so I think that's probably all I need to do on that. I think you guys should be set to go on 10.4 is what we just did. Any questions or concerns about that? Much easier than bootstrapping, isn't it? But it's nice to know bootstrapping is available and those dire needs. Mercy, did you have a question?
No, no question.
Okay. I'm going to go ahead and close that. And now I'm going to open up 11.2. This is an interesting section. I don't know if any of you got a chance to do much of the interactive. I know it's kind of that time of year where it might be getting hard to stay caught up with all your classes, but what you're doing here in 11.2 is you're doing hypothesis testing on two means dependent samples. And this means, two different words for means, what we're doing here is we're dealing with a single population and we're drawing two different samples from the same population. So in other words, we're not going to be drawing the average height of a group of women and then an average height of a group of men, because that's two different populations. We're going to be drawing samples from somehow they're paired, they're dependent. I think I talked at the beginning about probably the most interesting paired study was done in after the 1940s, after the Depression, after the dust storms that went through, all the Midwestern states all the way down to Texas and so forth. There were so many families that were in dire, poor straits that many families had to make the rough decision about dividing their kids up and sending them off to relatives that could afford to take care of their families because they were wiped out. Though the Depression followed by the Dust Bowl just really wiped out the farms. And so those people were desperately poor. Well, families got split up and even twins got split up. And so there were, a handful of twins, and someone had the thought hey, that would make a great research, seeing how twins differed in their adulthood, even though they were raised in separate homes. And they came up with some very, very unique things. But I don't want to get into that. But that's a very, very famous paired study because each twin was paired with their partner and compared to their partner. So another famous test, famous paired study was the freshman 15. And I think I brought that up too, that the freshman 15 study is all about the speculation that freshmen going off to school, not living at home, going off and living on their own, generally will gain 15 pounds in their freshman year of high school or college. And I don't want to go into all the reasons why that might be, but that could be studied. You could ask freshmen to come in and weigh themselves at the beginning of the year and then weigh themselves at the end of the year and see if there was any change and fluctuation in their weight. And so each person, as that study was the subject, they had paired data, their weight at the beginning of the year and their weight at the end of the year. So you need to be thinking about that you are looking at a single population, two different measures from that same population at different times, or somehow they are paired. Another study is looking at, and this would be more of a qualitative study where you're trying to identify the similarity or dissimilarity between husband and wives. So obviously, you don't care if husband A, matches up with some other person's wife. You want to have the husband and wife together to see if what areas they correlate on and what areas they don't. That would be another example. So I want you thinking about paired data. Okay, so I am going to go ahead and make that a little bit smaller. I'm going to try to do the StatCrunch ones. You have StatCrunch compute the differences by checking the differences box. This is just a reminder. I'm going to demonstrate that, but I can see where you'd easily forget that. So we've got that tip in there. And then we're going to do stats and select summary stats to compute the mean and standard deviation of the differences. We're going to do some real thinking here. So not that you don't think otherwise. I'm going to move this over so that I have more room to display my stuff in StatCrunch. Okay, I'm going to show it complete just so that I know how many places I have to do this. And, oh, we don't have a whole lot that we're doing. Oh, we do. Okay, so assume the differences. They've given us no context. We have no idea about this, but we just know that we have 8 different data, or we have a sample of size 8, and we're taking 2 different measures. X1 measure might be morning and Y measure might be evening, or we don't know what the measure is. We're looking at a mean of something. But anyway, so we're going to go ahead and open this in StatCrunch. And I'll move this over here. Okay, so I've got my observation. I've got X1 and Y1. This is, we're basically just our 2 different measures. So what I want to do, and this is a new prospect here, but you're looking at this and you are looking at mean averages. Okay, so we're going to go into stats and I'm going to go down to T-stats, but this time I'm going to go down to paired because I have paired data. This changes the menu. So now I can look at, well, my first sample is going to be in sample 1, X1, XI or X1. My sample 2 is going to be in Y1 or YI, whatever it is. And it said determine the difference. So this little notation here is the difference of each individual person in the population, whatever this population is. Maybe we're looking at the measure of height of turkeys before and after some, I don't even want to say exercise routine, but I'm going to say some feeding regimen, whatever. Anyway, so we're taking X1 minus Y1 for each pair of data. And that's what I did, is I'm saying X1 is sample 1 and Y is sample 2. So I want to check on the differences because we're going to do a different experiment with the differences. And so notice my menu here for the hypothesis is different. I've got this new notation that my null hypothesis is saying the mu of the D. In other words, the average of the differences what we're doing is we're finding the difference between 48.2 and 49.1, finding the difference between 49.7 and 49.1. We're finding each of these differences, and we're taking those differences, adding them up and dividing by 8, finding the average difference. There might be some above, that'll be positive differences, some will be negative differences, possibly. Who knows? And so we're checking to see if the average of the differences is equal to 0, or in this case, different from 0. You know what? I'm gonna let this go. I said the differences here. I'm gonna go ahead and click compute. I'm just gonna put this down here for now. But here are our differences that you will place in here. That's why we wanted to check the box. So Mercy, you don't have to do this by hand. We found a way that StatCrunch will do this for you. So we've got our differences here. You'd mentioned last time you liked having the differences. So now that I have my differences here, I want to find the average difference. I'm going to go into StatCrunch. I'm going to use summary stats. I'm going to do columns. And now I'm going to do differences. That's the column I want to look at. And I would just want to see what my mean and my standard deviation is. So when I do that, I came up with a mean of negative 2.1875, which is what we have down here, and a standard deviation of 1.8750. Yeah, or just 5. They wanted to only 3 decimal places. Okay, so we're going to use this that I already hit center, is the difference equal to 0? Oh, they wanted us to test to see if it was less than 0. So I kind of jumped ahead there. I'm going to go back and edit, and I'm going to make this less than 0. So when I do that, I came up with, boy, a really low t-score. Remember, we said between -2 or about -2 and 2, depending upon the size of your sample, etc. -3 is pretty darn low. And then when I look at the p-value, I've got 0.0061. Well, that is far less than our alpha of 0.05. So in that left tail, this data is way down in that left tail that there's only, less than 0.66% of the possible outcomes would be lower than that. Okay, so test that, blah, 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 we did. And so this is our null and our alternative hypothesis. We've got a t-score of -3.3. That's what that would round to. And then our p-value is 0.007. That's what that would round to 3 decimal places. Now we need to choose our outcome here. Are we going to, because it's in that tail, it says we've got an extreme difference here. So yes, reject the null hypothesis. There's sufficient evidence that the average difference is less than 0. Now compute the 95% confidence interval about the population mean differences of D1. In other words, we want to know just where can we be 95% confident that the true population mean will fall. We know that for this sample, it was at -2.1875. But maybe the next sample, it'll be a little off. So we want to be 90, we want to figure out where we can be 95% assured. So you know what? I'm going to leave that up. I'm going to go to stats, t-stats, paired data. Actually, yeah, paired data. And I'm going to put in the same thing I did before, X1 and Y1. And this time I'm going to come down here to the confidence interval, and I want to be 95% confident. Now, the thing is I'm 95% confident. Well, that means I'm going to have 5% confidence in split between the 2 tails. That's what 95% confident means. But we're doing because our test is a one-tail test, I'm saying that I would have to have 5% in the lower and in the upper, because I need some error in both tails to make sure that I come up with, to identify my limits, my lower limit and my upper limit. I have to have the tails to identify where those limits are. So if I want 95% confidence, that means I have to have 5% in the lower tail and 5% in the upper tail. So I really am looking for 0.9. This is not a big thing to me if you miss this. A lot of instructors don't teach that. They just say leave it at 95 because it's too hard to explain that, I guess. But I'm going to go ahead and click compute. And I find that I have a lower limit. I am 95% confident that the true population mean of this data, whatever this is from, for any set of data from this population, will fall between negative 3.44 up to negative 0.93. Basically, what I want you to get out of that is that entire confidence interval is below zero. So when it's below zero, I am 95% confident. I mean, zero is not in that. It's all the entire confidence interval is negative. Zero is not in that. So we are 95% confident that this is where it falls. And so, okay, I'm wondering if that changed. I'm going to go back and edit and see if they want us to do the 95 because that would be new. Yep, they're taking it this way. And it doesn't matter. It's all good. So just put in the 95%. Okay, so I'm going to leave that. I'm trying to think what okay, this is an actual application. And this is something I want you to be able to make sense of. And what I'm going to do is I'm going to open up a new table. And close this one. Because you're like, where's my information? This is a scenario where we have paired data, paired information, but we have summary information. Okay, in an experiment, 16 babies were asked to watch a climber attempt to ascend a hill. On 2 occasions, the baby witnesses the climber fail to make the climb. Then the baby witnesses either a helper toy push the climber up the hill or a hindering toy preventing the climber from making the ascent. The toys were shown to each baby in a random fashion. A second part of this experiment showed a climber approach the helping toy, which is not a surprising action, and then the climber approach. Okay. The second part of this experiment showed the climber approached the helper toy, which is not a surprising action, and then the climber approached the hinderer toy, which is a surprising action. So the amount of time the baby watched the event was recorded. The mean difference in time spent watching the climber approach the hinderer toy versus watching the climber approach the helper toy was 1.23 seconds with a standard deviation of 1.56. So in other words, the difference in time, we're assuming that they spent more time watching that climber approach the helper toy. I'm sorry, the hindering toy versus the helper toy. So basically state the null and alternative hypothesis, determine if babies look at the hinderer toy longer than the helper toy. Let U of D represent the difference between the mean hindering, the average hindering time with the hinderer, and the average time with the helper. We want to see what that difference is. That's our, where hinderer is the population mean times baby spent watching the hinderer toy, and U helper is the population time baby spent watching the climber approach the helper toy. So you're looking, basically, you're looking where's HO and H1, whatever. HO and H1 have this new format. We're testing, remember, no change is the standard. So we know that U of D equal to 0 is going to be we're assuming there's no difference. That's going to be our null hypothesis. And we're looking to see if, that we can speculate that the difference is greater than 0. In other words, that the time watching the hinderer was higher than the time watching the helping. And I can kind of see that because you're trying to see if children, I mean, they would be kind of alarmed. They would expect, that that toy would approach that hindered toy and shove it over or something because that's might be what they observe. Or they're really concerned for them because the last time the hindered toy came near this, this rock climber or whatever, mountain climber, the hindering toy knocked it over. And so it's suspicious waiting for it to happen again. They're checking to see that. Is the baby even aware of any of that possibility? Or sometimes it gets knocked over, sometimes it doesn't. And, the helping and the hindering toy have nothing to do with it. It's just random. That's what they're checking to see. So that's why we would choose that particular option. Never is the hypothesis going to be greater than or less than or not zero. So we can eliminate C, E, and F for sure. Okay, assume the differences are normally distributed with no outliers. The difference in the amount of time the baby will watch the hindering toy versus the helper toy is greater than zero and at a significance level of 0.01. So that's what we're testing. Also, we don't have to, because we know this is from a normally distributed data set, we don't have to do that test for outliers. We don't have to, check to see if it's normally distributed, but we're using that, what do I want to say, either the histogram method or the box plot. Okay, find the stats. So we're going to go in here to stats. I'm going down to T-stats again, and again, I'm looking at paired. But this time, sorry, I did something wrong. Stat, T-stats. This is going to be you know what? All of this is calculated for us. We already know the difference. I don't have to put in paired data. So I'm going to go in here and I'm going to treat this. I should have done that on the last problem too. I'm going to treat this as, one sample data. So I'm going to go into stats, one sample with summary, and I'm going to put the summary information that we have about these differences. We were told that we had a mean time of 1.23 difference of time difference, and that the standard deviation of the differences was 1.56. And we had a sample size of how many babies? 16 babies. And the rest of this we can leave, we can leave the zero in there, but we're looking to see if that difference is greater than zero. That's why we chose this one here. So that's what we're testing. The HA is going to be greater than. So at this point, I can go ahead and click compute. And I came up with a t-score of 3.15, whatever. And our p-value is 0.003. That is way down there. That's less than 0.5% chance that you would get that outcome if it was just totally random, which one the baby spent more time looking at. So from that, you could draw a conclusion that, hey, little babies understand something about social graces and so forth. They recognize it when they see it, and then they're alert to it. So we would reject the null hypothesis. The difference is not equal to zero. There is sufficient evidence at the 0.01 alpha or significance level to conclude that the difference is greater than zero. What do you think the results of this experiment imply about babies' abilities to assess surprising behavior? There is sufficient evidence that babies have the ability to assess surprising behavior or to assess safe behavior, concerning behavior, or unusual behavior, whatever, however you want to put it. Is that okay? That's about as much as I want to go. We've got about 15 minutes left. I don't really feel like I need to demonstrate the last couple because you've kind of should have a good understanding of that at this point, especially if you've done the interactive. And once you do the interactive, I think you should be in pretty good shape to do information with our paired data. You can either look at the differences, calculate the differences, either in StatCrunch or, on your own if you want. You can look at the differences and then just do a one sample test. Or if you have raw data, if you do have raw data, you can just put the raw data in, leave the raw data, and go to paired data, paired information, and then find the difference. And just run the paired data. Let the paired data do all that work in the background. Are there questions on that?